Sylvia is here.
Sylvia is back. How about Jasper and Anki?
Jasper is here.
Okay, glad to have Jasper back. Okay, and I'm sure Anki is there. Okay, now let's go ahead and start the session for today. The session for today, I should say, it's initially it sounds very easy, but at the same time, in practice, you are gonna work with that a lot when we just go to the Sigma lab sessions that we have. And over there, you will see that the practicality and applications of the things that you're going to learn today, which is going to be the polynomials, is going to be of tremendous, I should say, importance. Then we say that the lesson is going to be about the polynomials. Then the lesson, as I said, sounds a little bit, I should say, much easier compared to the things that they finished on the previous chapter, which we talked about, I should say, the optimization and the local and global maxima and minima. This one sounds easier, but bear with me, you see the importance of that by Monday next week, hopefully in our Sigma Lab sessions. Okay, but what do we mean by the polynomials function? You saw that when we talked about the functions, we have talked that in different sense. We saw that I'm just going to talk about, let's say, for example, different type of the functions. Imagine that. We talked about the functions like this. We said that f of x. We talked the function as a transformation that it takes your input variable x and transforms that into something different and something new, and you're just going to take that one. And we say that, for example, functions, we talked about, for example, the square root of, for example, x. It was these functions that we talked about. For example, we talked about other functions. For example, we talked about the f of x. It was, for example, a trigonometric representations of the single variables which you had. For example, you had the sine of x. We also, in functions 11, we saw some other different types of the function. For example, we said that g of x can be an exponential function. We saw that, for example, e as a Neper number, for example, into, let's say, for example, x as a different functions that, for example, that we saw that in the functions 11 course. And also, for example, we talked about a different type of other functions, h of x, that it was a logarithmic function that we said that, for example, we can represent it as, for example, logarithm of, let's say, for example, x. You will see that these things that we talked about, that I should say, on the functions 11, all of them were a single variable functions, because in all of them, we said that the transformation of f acts on only and only one single variable, which is going to be the x itself. And we saw that, for example, on the first one, we have the x, which for all of them, we had different type of the functions. We had the logarithmic functions, we had the exponential functions, we had trigonometric functions, and we had, I should say, the square root of that, I should say, single variable. In all those functions that we talked, we had different formats of the transformation. For each transformation, by the transformation, you may recall that we mean a change into something, a drastic change of a single variable which we have. We saw different formats, the trigonometric and many different formats. But right now, we are going to focus on a different type of the functions, which we call that function, I should say, a polynomial function, which in the polynomial functions, which is going to be the topic for today. Although it seems very simple, but as I said before, in practice, we are just going to benefit from these functions a lot. In the general format of this function is very simple. The general format of this function, we represent it in a very simple way. We said that this function, as a polynomial, takes a very simple format. A polynomial function, as you will see, it's a transformation of only one single variable function. At this stage, at advanced functions, 2 of them. That's the first characteristic of this function. It's a transformation. It's a transformation only of one single variable. And this one is represented like that. We say that, okay, it's going to be written in this way. We said that in this notation, guys, I'm just going to type something here. I'm just going to write something on the top right corner of the text. I say A represents the coefficient and X represents your variable. Okay, and now saying that, I'm just going to go back to write the general format of these functions. We say that the f of x, it takes this form. It becomes a subindex n x to the power n plus a subindex n minus 1 x to the power n minus 1 plus a subindex n minus 2 x to the power n minus 2. You see that you can continue this trend to go to plus. Let me erase this part. Plus, you take, as you see, you take many different terms. You go all the way here to just get a1 to x1 plus a0, which it can be sent that it's going to be to the x0 to the power 0. Then you see that based on the things that you learned from, I should say, the elementary functions, we know that here x to the power 0, any number, any variables to the power 0 is represented by 1. Then you can write just a naught. But what do I mean by this type of writing a function? First of all, we saw that a polynomial functions that we are going to talk right now, it's a transformation of one single variable, and single variable which we have, it's denoted by x. You see that here. I have my single variables are as x. I have x here, I have x, I have x, I have x, and I have x. This is my single variable, which randomly it may change. At the same time, you come here and see that I have some coefficients. And also, before I just go to the coefficients, you see that each single variable has a power as an exponent. You see that, for example, x, its power is what? Is n. The power here is n minus 1. The power of x is n minus 2. Here is 1, and here is 0. So far, so good, everyone, huh?
Yes.
And you see that for each individual, I should say, single variable, I have assigned a coefficient. These ones are the coefficients. These ones are the coefficients that you see that it all corresponds to each single variable. And in order to show this correspondence, I have denoted that, for example, by a subindex an. You see that n minus 1 corresponds to n minus 1 the power. It only denotes that this coefficient belongs to this single variable, which has the exponent as n minus 1. It doesn't mean that these coefficients has the power. It means that these coefficients corresponds to this variable. It means that they are from the same group. Normally, okay, let's give some examples of these kind of stuff. You see, guys, n. As I said, n is a single is an exponent of single variables. In the polynomials, listen to this. This is very important. In the polynomials, n, which is the power of the single variables which you have, and all belongs to what? All belongs to the natural numbers. Which natural numbers? You know that it's the set of the numbers which starts from 1 to 2, it can be 3, it can be 4, and it goes all the way to, let's say, n. N can be anything, 1,000, 2 millions. You see that the natural number is the typical number, the plus integers that you have. 1, 2, 3, 4, 5, 1,000, 1 million, 2 billion and 500 million. It can be anything. Then you see that the n cannot be negative, and n has to be always a positive integer. That's why I denote n as a number which belongs to the natural numbers. You see that. Then as a result, you see that then these functions that I denoted previously here, these functions which I denoted them here, they are not the polynomial functions. Let me write, not a polynomials. Because a polynomial has to adopt this format. For example, I'm going to give some examples, but before I give some examples, I'm going to just say one last words about the exponents that we have. And as you will see, the exponents that we have, n is denoted as what? N denoted as the power of your polynomials. You see that we start in a descending format. We start from the bigger n, then we start step by step to go lower. It's like this step. For example, n is here, for example, 4. Then you go to a step 3. Then you go one step further to go to 2. Then you go to a step for number 1. Then you go to 0, which is going to be the ground. You see that it's like the stairs, that you descend the stairs from the top of the stairs going all the way to reach the ground, which is going to be this level then. The bigger power which you have, the highest number of the n that you find in your polynomials, it denotes the power of the polynomials. Power or degree of the polynomials. Now, I'm going to give some examples. As an example, imagine that I ask you please to write a polynomial of degree, let's say 4. It means that if the degree is going to be 4, I say the degree is going to be 4, then it means that the polynomial that you right now come to write it, it takes this format. It takes as f of x as a polynomial, the degree is going to be 4. It means what? It means that the higher power of n should be 4. Then as a result, I'm just going to write it here like that. A sub index 4, it's going to be x to the power 4 plus a sub index 3 to the x to the power 3 plus a sub index 2 to the x to the power 2 plus a sub index 1 to the x plus a naught. I removed x0 because x0 is going to be 1. You see that that's a typical example of the polynomial of degree 4. You see that again here. The thing that I have, you see that this one, it starts from 4, goes to 3, goes to 2, goes to 1, and goes to 0. And also, you see that each one has a coefficients a4, a3, a2, a1, and a0. But the problem that we have right now here is that a4, a3, a2, essentially the coefficients, they can be in the numbers. They can be any numbers. We know that we have a restrictions on the power. The power has to always be a natural number, but the coefficients can take any format. For example, this one, I'm just going to write f of x. I'm going to have some numerical values for my coefficients. And I'm going to say that f of x equals to a4. I can come with the a4 as something, let's say, for example, like square root of 2 times x to the power 4 plus. For a3, I can come, let's say, for example, with a number as easy as pi, x to the power 3 plus. For a2, I can just come anything. For example, let's say 10, for example, x2. And for a1, I can write, for example, 0, x plus and for a naught, a0, I can write that any number I want. I can write, for example, let's say 5, anything. Then you see that the coefficients which I have adopted in this one ranges from many different choices, from a squared one to a number as beautiful as pi, to a number as 10, even it can be 0, and a positive or negative number. Then you see that they all denotes, I should say, a natural number. Sorry, they all denotes any type of number which you want to decide to have, I should say, as the coefficients of your polynomials then. But the thing which I have to highlight before I go to the next page is this. Guys, again, remember, the power of your polynomials, these ones which I highlighted in red, as you can see, these ones should be natural numbers. And that's very important. If you have this in mind, I'm just going to go to the next page. I'm going to introduce you a different, I should say, for example, a function. I'm going to write you some functions, and you please let me know that if these functions are polynomials or not. I'm going to say, for example, the function f of x, which is a transformation of one single variable, is 5 times x to the power 7 plus square root of 3 times x to the power, let's say, 4 plus 2 to the power x minus 17 times x to the power of, let's say, square root of uh, 8 plus the natural number e. That's going to be an example. Okay, I'm going to ask you the question, guys. Is the function which I have written here, is it a polynomial? If it is, let me know what is the power of that polynomial. Guys, are you there? Lara, Sylvia, Anki, Jasper?
Yes.
Yes. Okay. Is it a polynomial? Or it is, what is the power of that, degree of that polynomial? Who says it is a polynomial? Who says it's not a polynomial?
I think it's not polynomial.
Lara, you said it is not?
Yeah.
Why?
I have 8.
That's right. That's right, Laura. Look at that. Laura is right. Look at that. This is not a polynomial. Why? Because in order to check that you have a polynomial, you have to always go back to the trick which I told you. I said that the powers which you have on your single variable, n, n-1, n-2, the power n should all belong to the natural numbers, which means 1, 2, 3, 4, 5, something like that. It doesn't matter what values you get for the coefficient. The only thing which matters is that the coefficients, the power should be a natural number. The first one, the first term, we have 7. The second term, we have 4. This one is 5. This one is great because I know that this one, the power is 1. Then it means that this is a natural number. For this one, for the e, I know that this is x to the power 0. I know that this is still the natural number, although I know that it's that intercepts. I assume that this one, it makes the polynomial. However, when I come to this term, I see that the power which I have here is what? Is square root of the 8. And the power, as you see, square root of the 8 does not belong to the natural number. Then as a result, this one is not a polynomial. Does it make sense to everyone?
Yes.
Great. Now, I just go to the second example. I say that I have another function, g of x. It's going to be like this function. I say sine x, x to the power 2, plus square root of 3 x to the power 1, plus, let's say, 22 divided by 5. Okay, how about this term? Is it a polynomial or not?
Yes.
It is a polynomial, huh, Laura?
Yes, it's a from.
That's right, that's right. Thanks, Laura. How about the others? Sylvia, Jasper, Anki. What do you think, guys? Anki and Sylvia, and also Jasper. Look at this one, guys. We have, for this term, we have square x to the power 2. And let's highlight the terms that I have. For this term, I have the power 2. For this term, I have the power 1. And for the last term, I know that that's just the intercept, and that's totally acceptable. Then it means that this is a polynomial because all the powers which I have, which is 2, 1, they are all belongs to the natural numbers. Then this one is a polynomial. But you can see this at the same time that the coefficients which I have, sine x, square root of the 3, and this one, they can have any format. They have no restrictions whatsoever. They can adopt any type of the format which they want, from the sine x to the square root of the 3, and also to an irrational number as 22 divided by 5. Then you will see that no restrictions whatsoever on the coefficients. However, we have the restrictions on the exponents and the powers of the variables, and that is that they have to belong to, I should say, the natural numbers. Okay, I'm going to go with the next function. I say that the h of x is going to be this. I say that it's going to be e, the natural number, to the power x, it's to the power 3, plus, let's say, sine x to, let's say, x to the power cosine x plus, let's say, put this as minus pi times e to the power of tangent of the x. Guys, how about this one? Is it a polynomial?
Yes, it's a polynomial.
This is a polynomial?
Maybe it's.
This one is a tricky one, huh? Let's say, oh, what happened to my whiteboard? Give me a second. Okay, look at this one. Okay, this one sounds very interesting. We just go from the beginning. We said that the first term, the power is 3. For the second term, the power is cosine of the x. And for the third term, we know that the power is going to be what? It's going to be x to the power 0, huh? And we assume that this is something which is accepted because it becomes 1 and it relaxes the restrictions that 0, it doesn't belong to the natural number. But look at these two terms now. For the first one, I do not see the restrictions on the coefficients. Although, guys, even for the previous one, in most of the text, they say that the coefficients has to be real numbers. But sometimes we say that, okay, because the coefficients is sine x, we may not think it as a polynomial, but at this stage, we relaxes our restrictions on the coefficients. Although we believe that the coefficients has to be real number, we relax that restriction here and we focuses our assumption that the power of these variables, the exponents of the variables has to be a natural number. We see that this one, the power is not a natural number. Because the cosine of the x, it's not a natural number. And then when I write it here, cosine of the x does not belong to the natural numbers, which they are a set of numbers, 1, 2, it goes all the way to the infinity. Then we say that this one is not a polynomials. But the polynomials that we had here, it was, on this example, it was this one. If we assume that we can accept the coefficient of our case to go to, let's say, for example, to be a sign of the x. Although in some of the textbooks, you see that they put the restrictions on the coefficients that it should be also a real number. But we focus our attention on the exponents of the variables that to be belongs to the natural number. Then I'm just going to go to the next page, give, I should say, the very last example. We just say that the f of x, it's going to be, let's say x to the power 2 plus 5x to the power, let's say, 4 plus x to the power 100. Guys, is it a polynomial?
Yes.
It is. Thanks, Laura. This is a polynomial because when we come back here and focus our attention on the powers of these single variables, we see that 2, 4, and 100 all belongs to the natural number. Then as a very last question, what is the degree of this polynomial? What is the degree of this polynomial? Huh?
Real number.
Sorry, what?
Really number.
That's right. But the degree is, we say that, guys, Laura, we say that the degree of a polynomial is the highest power which they have. Between 2, 4, and 100, which one is the bigger one? $100 is the bigger one, huh? Then we say that the degree of this polynomial is 100. You always go to search for the bigger exponents of your single variables, and you call that, it's going to be the degree of my polynomials. For example, as a very last example, which I'm just going to focus on that, is that in one of your Sigma lab, I should say tutorials, you will see that you're working with a function like this, g of x. It's going to be, for example, a2 x to the power 2 plus a1x to the power 1 plus a0. And you see that this is a polynomial. Yes, Laura?
Yes.
Yes, Jasper, Anki, and Sylvia?
Yes.
That's right, this is a polynomial because 2 and 1, they belong to the natural numbers. However, we call that the degree of this polynomial is how much?
2.
That's right, 2, because 2 is the bigger number in the exponent, which is going to be 2, and 1, 2 is bigger, then the degree is going to be called as 2. We are going to work with this one on the lab tutorials next week. Then we say that over there, how we can just, when we have, I should say, our observations, how we can find an inference and estimate these coefficients A1 and A0. That's going to be left for the labs, which we are going to run by early in the middle of the next week. We are going to fit a model into the polynomials of degree 2. Then remember, when we said that the degree 2, if I ask you, write a polynomial of degree 2, you have to just think of this format. Okay?
Okay.
Awesome. Awesome. Fantastic. We have done a great job so far. Fantastic job so far. Now we have a couple of minutes. Any questions, guys, so far?
No.
No? Okay, fantastic. I think I need to cover one more thing then we move on to do some exercises from the textbook, or you may have it for the homework for the textbook. But let's cover a third part of the polynomials, then how we just make an inference about the polynomials. There is one point I just want to talk about that, and the fact that's this one, that the polynomials, they do not have any asymptotic behavior. Okay, that's the thing which I just wanted to highlight that for you. But what do we mean by the asymptotic behavior? Have you had that, guys, in the function 11? Did you cover that in function 11 course? Asymptotic behavior?
No.
No? Okay. Look at this one. I'm gonna asymptotic behavior. Let me also write this one here. I'm gonna talk about that more by next session. But let's talk about this one. Asymptotic behavior. Behavior can either be one, horizontal, or two, vertical. Okay. What do we mean by the asymptotic behavior, either the vertical or horizontal? Okay. We're going to talk about, for example, look at, as I'm just going to give, I'm not going to go too much into the details of the asymptotic behavior, because you are going to focus on that term, on this behavior, when you're essentially next year, when you are in your calculus and vector class, then you talk about the limits at infinity, then you are going to see much more explanations of this type of behavior. But a very simple term, I'm just going to show that one simple example. Imagine that I have a function that f of x is these very simple, easy looking functions, that it's going to be 1 divided by x minus 2. This is a function that we have. Okay. When we have a function like this, that it's a rational function, because we call this is a rational function because it has a numerator and the denominator, we see that this function behaves something a little bit odd at point which is going to be x equal to 2. Then as a result, because x equal to 2, it's an odd number as a singular number. It's a strange number for this function. Why? Because you see that when you take that number and plug it into the denominator of that function, you will get to this term. You will get that it's going to be f of x becomes what? F of 2 becomes 1 divided by 2 minus 2. This is 1 over 0. And that's something which we hated in the math. We do not want to see any number to be divided by 0. It has lots of philosophical interpretation of it, but we don't want to take that headache. We avoid it. Then as a result, we say that the domain of that function, the domain, it's x, which belongs to the old real number. However, x is not equal to plus 2. That's what we have talked about, the domain of the function. I write d of f of x. It means that the domain of the function is the set of all the numbers which belongs to real numbers. However, x cannot be equal to plus 2. and I assume that that's going to be a set. That's why I have those curly brackets between those two arguments. Okay, and now what is a connection between the points that I got it from here, which is x equal to 2, and the asymptotic behavior? I'm going to show that to you in a second on the Desmos then. I should say, stop sharing the screen and go to share my screen with the Desmos for you then. Okay, now let me share the screen, goes to the Desmos, and I have the Desmos right now here. Now, look at this, what the function was. Everyone sees the Desmos panel which I have?
Yes.
Awesome. What did I have here? I had f of x. It is equal to what? It was equal to number 1, I assume, divided by x minus 2. It's correct, huh? That was a function which I had it over there. And you see the plot of this function, which is denoted here. You see the plot, huh? It seems that it's a very beautiful plot. However, you see that at one point, which it does not belong to the domain of this function, which is plus 2, we have a singular behavior of the function. And what is that behavior? You can see that behavior with a different plot, which I said that x equals 2 plus 2. Look at that. The x equal to plus 2, which is the plot, I should say, with the blue one, you will see that the plot, when this is plotted at point equal to 2 on the x-axis, as 0 on, you see that it's intersect with the x, which the plot is connected, you see that the plot of the blue one, it becomes almost tangent to the 2 wings of the function, which it goes to the infinity. You see that? You see that at point equal to 2, the function goes to infinity. You see, I can just go here. You see the functions goes all the way to nowhere. I can also small the function. You see that it seems that there is no end to the function. The functions at x equal to 2, the value, it seems that it becomes infinitely large. And that's what we call that asymptotic behavior. In this case, because I can represent that asymptotic behavior with the equation at the denominator of the function, which is x equal to 2, look at the denominator of the function. The denominator is what? It's x minus 2. If I put x minus 2 equal to 0, I get the function as x equal to 2. Then this function, which is going to be the blue function, shows the vertical asymptotic behavior of this function. We call that vertical because that point is normal, vertical to the x-axis. It makes the angle of 90 degrees to the x-axis. Right? And that's what we say that's going to be an asymptotic behavior. But what type of asymptotic behavior? It's going to be, let's say, it's going to be a vertical asymptotic behavior. Any questions, guys, so far?
No.
Everyone is fine with the concept of the asymptotic behavior? But no worries, you are not supposed to know about this one except to see that how these functions looks on the graph. But you do not need to just find them because this is not part of your course. Okay, now I'm going to also come back again and okay, let's see what else do we have. Okay, I think that's going to be enough of the things that I just wanted to highlight it to you. But let me see if I want to include some more examples for you for the asymptotic behavior. Let's see. I think I think that's going to be enough for this part of the course that we talk about just the asymptotic behavior, because with the horizontal asymptotic behavior we have to just go into the details of to find the limit when, let's say, x goes to infinity, which I don't want to do that for you at this stage because it's going to be advanced and it's going to be the topic for the next year. But essentially with the asymptotic behavior, that's what do we mean. The function goes to infinity at either one side or two sides, then it normally happens at the root of the denominator of the function. Okay, now I'm just going to go to share my screen before we just go for uh, the next break. Okay, guys, you see the chapter 3.1 of the book that we have? It's a simple review that what are going to be the asymptotic functions and what is not. The simple ones that we covered that in the class. However, you see that the point which I just wanted to make is this. For this function, that's a polynomial function. Look at these ones, the namings which we have here. For example, linear. If the highest degree of your polynomial is 1, you call that linear. If the highest degree is 2, you call that quadratic. If the highest degree is 3, we call that cubic. However, we should be fine for the course if we know that these terms, but number degree 4 is called quartic and number 5 is for the quantic. But we should be fine with the first three ones when we talk about the linear, quadratic, and cubic. Then the thing which I just want you to please is that, and also you see some typical, for example, plotting of these functions. For the linear, you see that's a line. For the quadratic, you see you have plotted that before. For the cubic, we plotted yesterday. And for the quartic, you see that. And for the quantic, you see a typical form of the graph of these functions. And that it goes to the exercises. Please, guys, do the exercises, which is going to be page number 127. Starts from page number 127 and go all the way, I should say, to the end of that chapter. Okay? Until page 128 then. Then it remains for the homework that we do that on next, we check that on Monday then. Okay?
Sir,
Yes.
you mean is from 127 to 128 is the homework?
That's right. Please do that during the weekend then.
Okay, we need to send you.
Yes, please. When you are done with the homework, please take a picture of it and send it to me on the Schoology.
Okay.
This homework is going to be very easy because that one is essentially the thing that it's incredibly easy. You do that, you see that it's much easier than the previous chapter. Okay, now the time is 11:07. Any questions, guys?
No.
No?
No.
If there is no question, please
Mm.
guys, take the next break. Then we come back, we just go to the lab sessions which we have. Please take a break. Come back here, I should say by 11:05, let's 11:20. Come back, let's say by 11:20. Okay.
Okay.
By 11:20, we start, I should say, our R sessions. Have your R ready when you join the class then. Okay?
Okay.
Awesome. See you guys later then, and good luck. See you by 11:20.